took a look at was how do you specifically find the electric field at a particular point in space with this vector addition. So E net equals E1 plus E2 plus whatever number of charges you have, and this was a vector addition process. And we kind of picked one point in space, and we very specifically wanted to know the direction and size of the electric field there. Now we're going to zoom out and see the forest for the trees, as they say. Okay, so we're going to not be so obsessed with one particular point. We want to be able to sketch an entire region of electric field and get a sense of what the electric field looks like all over. Of course, we're going to give up some precision for that, right? We just want to know, generally speaking, what the electric field looks like. So they're both valuable skills. Can you find the electric field at one specific point exactly? Or can you get a general sense of what the electric field looks like everywhere? So that's what I want to look at today, is that latter thing. And let me just pick an example to look at. It's a charge distribution called an electric dipole. So it's probably the very next most simplest charge distribution past a simple point charge. Now instead of having a single charge, we have two equal and opposite charges. That's called an electric dipole. And just so that I can kind of keep track of this, I'm going to color code them. You can do the same with two different colored pens, or maybe just a pen and a pencil, whatever you have. And, you know, there are plenty of problems in which you would be expected to find the electric field at a specific point. I just want to sketch the entire region. So let me give you a few rules of thumb to start with, so that you can do these yourself. The first thing I guess what I would do is sketch in the electric field of each one individually. So positive charges, wow, that's really light. Let me see if I can get a slightly, no, that's not any better. So positive charge, radially away everywhere into the universe, like so. And the negative charge radially inward everywhere in the universe. Now those are just the individual electric fields, but at every point in space, what actually is contributed is the net field, which is the vector addition of both contributions. So at first glance, this is going to look like it's going to be pretty hard to sort out, but if we follow a few rules and we look for symmetries, we can make enough headway to basically connect the dots about what happens everywhere. So let me give you a few tips to go by. The first of which is about mapping scale. This is the first and oftentimes one of the very most useful things about electric field map. Let me give you an example. So I have a point charge. Now, of course, the electric field it makes is everywhere, but I make a decision to draw 8 radial lines to represent that field. Now remember, we learned that the line density is proportional to the strength of the electric field. So basically, if the lines are closer together, we expect the electric field is stronger, and when the lines are further apart, we expect the electric field to be weaker. That was the whole beauty of the whole scheme of radial lines, is that when you're closer by, the lines are spaced closer together, and that's meant to indicate a stronger field. And when you get further away, the lines get further apart, and that indicates a weaker field. That goes right along with the fact that the electric field is itself inversely proportional to R squared, which is that inverse square law. So that's something we already know, but what does that have to do with anything in terms of new information? Well, now that we have not just one charge, but multiple charges on the same map, then we have to have a consistency. Let me give you an example. Let's say I had another charge on the same map that was twice as large. Well, if I chose to draw 8 lines out of that as well, I'd have a problem. Oh, I should have written down the whole formula here. Let me do that. The electric field is KQ over R squared. So here's the thing. If I went to the same distance from this charge, and I just visually looked at the spacing of the field lines, and I saw that they were the same as this, I could fairly conclude that this field and this field are the same. The line density is supposed to represent the field strength, but obviously that's not right, because if the charge is twice as much, then at the same distance it should be how many times the field? Twice. It's twice as strong. So if you're a given distance away from a charge that's twice as much, it is twice the field strength. But the map right now is telling me, because I'm looking at the line density, that the field strength is the same. So I can't draw 8 lines to represent Q and also draw 8 field lines to represent 2Q. What do I have to do to make sure that the line density makes sense? I have to
add lines.
I have to add twice as many lines, that's right. So that way, the line density is twice as much. So if I pick Q is 8 lines, that's the only free choice I get when I'm starting my map. Is that the very first charge you put down, you get to choose how many lines are going to be represented by that. But then, if you have 2 times that charge, you have to have 2 times as many lines. Essentially what you're doing when you put down your first charge is you're picking a scale for your map. Essentially, the amount of charge divided by the number of lines that are attached to that charge has to be a constant through your map. That's like the scale of your map. So this is not just something for these specialized new maps, these are also road maps. Okay? I know you guys maybe don't have paper road maps anymore, but I think on the bottom of Google Maps it still shows this. Okay? So it'll tell you that on a given map that 1 kilometer equals 1 mile equals 1 inch or something like that, right? So that's the scale of the map, right? That 1 mile is 1 inch. It's not a full-size map, right? Otherwise it'd be as big as the whole thing you're driving, okay? So a map has a scale, 1 mile is 1 inch. Now, if 1 mile is 1 inch at this part of the map, it's also true on another part of the map. That's the whole thing. You depend on a map for consistency. Maybe sometime when your friend is drawing you a map on the back of a napkin, I don't know if this is a thing anymore, because now you just give someone the address and they punch in their phone, but when you draw a map for your friend on the back of a napkin, you tell them, oh, this is not to scale, right? because, 1 inch is a mile in one place and 1 inch is 10 miles in another place. But generally speaking, if you have a professionally done map, you depend on the scale as being constant, right? Now, it doesn't have to be constant from map to map, right? You might have a map of a town where 1 inch is 1 mile, but you might have a map of the entire country where 1 inch is 100 miles, right? Or 1,000 miles, whatever. But you don't have to have the same ratio on every map, but on a given map, it has to be constant, right? So your very first charge, you get a choice, and then every other charge that goes down after that, you don't have a choice anymore. You have to scale. If you have more charge, you have to have more lines. If you have less charge, it has to have less lines attached to it. That's the only way you're going to be sure that your line density is consistent across the entire map. So that you can depend on when the lines get closer, the field is stronger, and when the lines get further apart, the field is weaker, okay? So just remember, this ratio has to be a constant on any given map. Not between different maps, but on any given map, okay? So, for my situation, how does that apply? Well, I actually have equal and opposite charges, so I'm going to draw 8 lines out of both of them. I could draw 16 lines out of both of them, I could draw 1,000,000 lines out of both of them, but whatever the number is, it has to be the same for both of them. Is that okay? Does that make sense? Okay, so it's not that exciting for my map right now, but on some of the homework problems, you'll definitely need this information, okay? The other thing that is very helpful to drawing these maps is the fact that as R approaches 0, the contribution by of an electric field becomes arbitrarily large. You can see that right in the equation. When R approaches 0, E approaches infinity. So how does that help me? Well, E net, let's say I'm really close to charge 1. It's going to look like this. So really close to charge 1, the electric field of charge 1 is definitely dominating the situation, and essentially I can neglect the other one because its contribution is going to pale in comparison. So what does it tell me is that E net becomes basically indistinguishable from E1 when you're really close to E1. So that's also something helpful that you can do, is know that your net field is not going to deviate very much from the field of that single charge when you're really up in the face of that single charge. So with that, let me get my map started. So I'm going to draw the overall field in black. I'm going to draw 8 lines attached to each charge. And when I'm very near the 2 charges, the field is indistinguishable from that of the charge itself. Got one there. There we go. So that gets the party started, and now I venture off into the regions where I am roughly, the same distance from both charges. At least they both have significant contributions if they're not entirely equal. And I do need to think about vector addition, okay? Are there any questions before I do that? Yeah.
How close are we talking for R near 0, like?
Well, there's no magic
tiny?
cutoff, of
Okay.
course, but we're also drawing a very general sketch,
Okay.
right? So, we're just getting. Technically, it's true that the moment you leave the charge, the field is going to be, this is going to be non-infinite, so this is going to affect it somewhat. But again, the bend will be how it changes is going to be slight, and it's not going to show up visually, right? So we're just doing a general sketch here. Okay, so now that we have to consider the vector addition, we might do some symmetry axes to kind of help us. Probably the easiest axis to do is the one that runs along the two charges, because there it's definitely, the vector addition is going to be at least one-dimensional, right? Contributions are right or left, and that's it. Does that make sense? So, first of all, in the middle, both charges agree on which way the field should point. This one wants it to point right because it's away from a positive charge. This one wants it to point right because it's toward the negative one. So we're going to get a strong rightward electric field between them. Both charges agree it should point to the right, so it's definitely going to point to the right. The two charges disagree on the outsides. So out here, going away from the positive charge is to the left, but going towards the negative charge is to the right. So there's a left versus right. I'll label this one here. Are they going to cancel? Do you get 0?
No,
No. Why?
they're not right on top of each other.
They're not right on top of each other. Which one are you closer to?
Yeah.
Positive one. They're equal charges, so at equal distances they have equal influence, but you're not at equal distances to them. You're closer to the positive charge, it's always going to dominate. And so we can conclude that the net field in this region is to the left. It's going to just be slightly weaker than if it was just the positive charge there alone. And by that same logic over here, of course, we're closer to the negative charge. So the net field points inward. It's just a little weaker than if the negative charge were there alone, because the positive charge is, of course, going to take a little bit of the edge off. Okay. So we've just finished taking care of the symmetry axis that runs along the line the charges themselves sit on. Okay, are there any questions on that? Okay, so now we have to move off axis, and I will suggest another symmetry axis, which I'll call the perpendicular bisector. So that's a line that runs perpendicular to the line that the charges lie on, and it runs exactly equidistant from them. Okay, so that is the next symmetry axis that this situation would have. So let's take a look at some arbitrary point along that line. We have a contribution from the positive charge, which is of course always radially away, so points like that. And we have a contribution from the negative charge, which always is towards it. So those are our two contributions. Now, what can you say about the sizes of those two contributions? Which one is larger?
At one point.
They should be equal.
They should be equal because
The middle, yeah.
why?
Same distance.
Same distance from the same charge. So there's nothing there that would make one larger than the other. So they're the same size contributions, but of course the fact that they're kind of diagonal adds a little extra twist. So let's work it out over here separately. We have this one like this one like this. Their sizes are equal because you're the same R, same charge, but because of the way that they point, it's not necessarily going to cancel, right? In fact, you guys hopefully from Physics 1 have some kind of intuitive sense of vector addition. What's the direction of the net field going to be here?
Horizontal.
Horizontal, that's right. So for those of you that don't see it, we would break this into components. E1 has a rightward and upward component. E2 has a rightward and downward component, which apparently I didn't draw this very well. And what happens is that the y contributions cancel, or I guess I haven't said a y-axis, but the vertical contributions cancel, and these reinforce. So what remains is a horizontal net electric field. Question?
Yes, do they double? Because
Yes, you can say that E net is going to be 2 times the x contribution of either one, because essentially the 2 x contributions are going to be equal. So let me sketch that in over here, something like this. And I should point out that that argument holds anywhere along this perpendicular bisector, right? And so I can be safe in knowing that anywhere along this perpendicular bisector, the electric field is horizontal. What's the only thing that's going to change as I move further away? The electric field is still horizontal, but what happens?
Strength of it is gonna.
What's that?
The strength is gonna go down.
The strength is going to go down because you're getting further away from both charges. So those x contributions that are reinforcing are themselves smaller. And so let me just sketch a few examples here. Yes, let me do it over here too. So on and so forth. So hopefully I haven't been too imprecise. So at this point, I think I'm ready to connect the dots. I'm going to try to connect the dots. So what I realize, of course, is that if the electric field has to go from radially like this, very near the charges, to the all having to point horizontally by the time they cross through the perpendicular bisector, there's really only one way to connect this. So let me try it. I guess this one didn't have a friend because I already connected everything. So that's basically what the field looks like. This is going to be your plastic field. We're going to see this field a ton, and so it's an important case to do. That's the electric field, the net electric field surrounding an electric dipole. So I want to point out the features. I kind of call it as having like a lobey shape, okay? So it kind of has these 2 lobes. But where they ultimately came from was the vector superposition of the 2 radial fields. What we have, the features, are a relatively strong electric field in the region between them. And that is again due to the fact that in the region between them, the electric field from the positive and negative point the same way, either totally or mostly, and so there's going to be a relatively strong field between them, and that's of course evidenced by seeing the field lines close together, so it was nice that it came out in the sketch. Over here, we notice the field lines are pretty far apart. That tells us the field is weak, and of course we know why that is because out in those regions, the 2 charges are actually more canceling than reinforcing. And then, looking from along the perpendicular bisector, if I've done this right, which is a big question, let's see. Going out this way, the field should weaken, right? We already said that, and I think the field lines have gotten further apart, at least this side. Here, I think it's not quite as well. Should have drawn it more like this. There. So I have the field lines getting further apart as I move outward along the perpendicular bisector. So you can see that the field lines are getting further apart as we go this way. Okay? So we can certainly understand it thinking in the individual level, or all that information would be accessible to us right away if someone gave us that map, right? So we could just look and see where the electric field is stronger or weaker. okay? And I should mention also that since I happen to have equal and opposite charge, what that means is that the 8 lines that leave the positive charge will all connect with the 8 lines that have to go into the negative charge. The one exception, of course, is this one. This is the one lobe that essentially never makes it back around. So this one goes to infinity, this one comes in from infinity, okay? Now, on the homework, you may have maps where there doesn't happen to be an equal amount of positive charge and an equal amount of negative charge. That's okay. It just means that there will be some lines that are not paired up. It means that some lines may go to infinity and not connect to the other charge, okay? Or something like that. So be aware of that. This is a special case where there happens to be equal and opposite charges. So basically, aside from this one special line, everything that leaves the positive charge happens to go into the negative charge. That's not always the case, okay? Are there any questions on this, what I just did? Yeah?
So on the perpendicular bisector, the net electric field is always to the negative charge?
It's not toward the negative charge, it's always horizontal, right? So that's different from directly pointing towards it, right? The blue is the field of this one alone, that's always directly towards it, right? So right here, for instance, it's like that. But the presence of the positive charge makes the net field go like that, right? Which is a completely different direction. So it makes the field on the perpendicular bisector always point to the right, not necessarily directly toward the negative charge. Does that make sense? Okay, any other questions? I'm asking if you have questions more today because I have the stomach flu and I have no idea what I'm even saying half this time. So please, if I say something that completely doesn't make sense, just let me know, okay? Yeah.
So if they're not equal to each other, then that those horizontal lines would wrap back around.
Well, so for example, if this were a larger charge, then you could not safely say on the perpendicular bisector that these two contributions were equal in size, right? Let's say if this was larger, you'd have this arrow would be bigger, right? Be something like that. And the vector addition of those two would definitely not be horizontal. It would be still dominated, of course, by this larger charge. So the net field might look something like this. So if that were the case, what you'd find is it's more or less looking like this, but the point at which the field lines that left this charge and connected to this charge went horizontal, which is to say when they both had equal contributions, would be more like closer to this one, right? So in order for the two charges to have equal effect, if they're unequal charges, then you have to give the smaller charge some advantage. So it has to be closer, right? That's actually one of the primary things to realize in homework number 1 as well. So I'll give it away right now. If you have two charges that are unequal in size, unequal charges, if you want them to have equal influence, you have to give the smaller charge an advantage. You have to be closer to it, right? So what would happen, the field would look something like this. So let's say this is plus 2q minus 2q. What you'd find is that the point at which it looked like that would be much closer over here. So it'd be kind of like that. It still would have that lobe shape, right? But it'd be much more skewed like that. And I should also mention that because there are twice as many lines out of this one, you'd have many unpaired field lines, right? Out of the field lines that came out of this one, only half of them would have to connect to this one. The other half would have to go to infinity. Does that sort of make sense?
Mm-hmm.
Yeah.
Why are you bringing the smaller charge closer to
What I just meant was that if you want a point where the two charges have equal say, if this charge is bigger, you have to be closer to the smaller charge in order for them to have equal say, right? So if one wins the competition on Q, the other one has to win the competition on R in order for their E's to be the same. Okay, so this is our first field map, and this is just one that I wanted to do one for you that has a, just to get the ball rolling. Maybe Kyo will talk about this more during the SI session. So just to give you a little preview of where we're going, one of the things you can do is you can smear charge into other configurations besides just point charges. So the focus of homework number 1 is certainly only point charges. So this what we say is discrete collections of point charges. So you have 1, 2, or 3, or whatever point charges. But you can also take these point charges and smear them out like butter on toast, where instead you can put them kind of onto these slabs, these plates. So this is what's known as a finite parallel plate capacitor. Now, as to why is it called that? Well, this is actually going to turn out to be an electronics component that we'll start putting in circuits later in the semester. But for right now, all you have to do is say it's an interesting configuration of charge. And what you can slowly imagine is that since we've sort of slightly morphed the charge configuration, we're going to slightly have morphed the electric field configuration as well. So imagine these plus charges and the plus and minus charges with little lumps of Play-Doh, and you just smashed them and made them a little flat plate. Here's what it would look like. It's not really so different. It hasn't really changed that much. So you can see the field is still strongest between the charges, and you can see that the field is still weakest out here. But you can also see that what I've done is essentially starting to create a haven in between there where the contributions of the two electric fields is roughly the same. And this is a special name of a type of field called a uniform field. And I should say it's approximately uniform at this point. It's not perfectly uniform. But as we will see later, in fact, not too much later, in homework number 2, in fact, let me show you the final transformation of this. But it's a good juncture to kind of mention what happens at the end of the day. So imagine that we concoct this thing called the infinite parallel plate capacitor. So this is where we hypothetically smear charge onto the two plates, and we smear it so that it's infinite. So it's infinite going out in this direction, which I can draw on the board, and it is also smeared out this way, although I don't know how to draw that. This is not an infinite line, this is an infinite plane. And it turns out if you do that, now, first of all, you might say, wait a minute, this construct doesn't exist. Like, why would you bother with this? There's no such thing as an infinite parallel plate capacitor. It wouldn't fit into our finite universe. Well, it is a useful abstraction because it creates the simplest electric field possible. This is an actual uniform electric field. So what we've essentially done by extending the edges of these plates to infinity is we've never let the electric field weaken along the perpendicular bisector. So over here, the field got weaker along the perpendicular bisector because you're getting further from the charge. But here, as you move along here, you're always the same distance from the charge. There's never any getting away from it. And as we will also learn later, the field outside here is not only weak, but has actually gone to 0. Now, we will actually calculate the mathematical details of this later and show this all and shore it up. But the main thing I just wanted to discuss at the moment was what's the deal with the uniform field. So a uniform field does make its first appearance on your first homework. I don't say where it comes from, so this was just a convenient excuse to give you a preview of where it comes from. But in several problems you are given that you have a uniform field. And if you see that you have a uniform field, you should, say hooray, because it's literally the simplest electric field that you can have. Uniform field is constant in size and direction everywhere. Now, yes, you need some really contrived charge configuration to make it, but that's for good reason, because if you just had a simple point charge, the electric field is most definitely not uniform, right? We said that it's an inverse square law. So it shouldn't be any surprise that we did some bizarre configuration of charge to make an electric field that never dies. It's always the same strength everywhere. Now, why is this a cause for celebration? Well, if you have a constant electric field, if we go here to this equation, if we have a constant electric field, what does that mean about the force that it will exert on a charge? Constant force, not a force that changes with distance. And then we go to F net equals ma, and if we assume that the electric force is the only force, what does that mean about the acceleration?
Constant.
It's constant. And if you have constant acceleration, then you have access to a series of equations called what? Constant acceleration equations. Some of you may know them as the kinematics equations, although I hate that term because kinematics just means description of motion. The kinematics equations don't describe all kinds of motion, they describe one kind of motion, and that is constant acceleration. So, you will find a problem, I think at least one problem on your homework number 1, which is basically just an excuse for you to review your constant acceleration equations. It's essentially a weird way of asking you a projectile motion question, except instead of the acceleration being 9.8 meters per second squared, you can calculate the acceleration by knowing the field, just like this. If you get given the field, you can find the force and acceleration. Okay? So it's a cause for celebration when you get a uniform field because you get to use the constant acceleration equations. Now, just as a reminder, I mentioned this before, what if you don't have a uniform field? Which, again, is more the normal. You're lucky to get a uniform field, but what if you don't have a uniform electric field? Then that means that the electric field, force, and acceleration are not constant, and so you do not have access to the constant acceleration equations. You should not use them. Absolutely do not use them. They will not work. But, does anyone remember from the other day, what's the method that we use that works very well whenever we have some crazy acceleration profile? Energy, that's right. So, the energy method is going to be our friend here. That's going to be the main topic of homework number 3. And of course, the one thing that you do give up that is not coming out of the energy method readily, what's the one thing that you can't find in energy?
Time?
Time. It won't tell you how much time it took to do things. So, both methods, of course, have their place, right? So, energy method can very quickly and easily deal with non-constant acceleration situations, but it can't give you time. And then, for the force and acceleration, they can give you time, but they're very limited in what they can accomplish when the acceleration is not constant. So, I hear a lot of rustling. Is that clock slow or something? Oh, okay. So I have a couple minutes here. So, you may be surprised. I've already hinted at the energy method twice. Why am I saying it's not until homework number 3? We do have a few orders of business to take care of first. That's what your homework number 2 will be about. So what is your homework 2 about? We're going to get conceptual with conductors and insulators. And we are going to have to talk about things like this and things like this when we have these continuous distributions of charge, and how do we calculate the electric field caused by them. Okay? So that's what homework number 2 is about. So let me see what I can get done with that today. This definitely closes out homework number 1. So homework number 2 is going to be this weird mix of totally conceptual and heavy calculation. So let's start with the conceptual stuff. I'm going to prioritize that because that's what's going to be on your lab next week, the electrostatics and charging by induction lab. So I'm going to start off with talking about something called the triboelectric series, or triboelectric effect. We are actually putting ourselves in the shoes of the very, very earliest human beings ever to notice electricity was something that wasn't just confined to lightning. So, since ancient times, people have noticed that when they rub two things together of different materials, sometimes you get what they call static electricity. Okay? It was not understood for a long time, but nonetheless, it was noted. So what happens here? You have two objects. I'll call them objects A and B. And they're both neutral objects to start with. And it was noticed that when you rub them together, and I don't know how to draw rubbing, something like that, it was noticed that they suddenly attract each other. And the name given to this phenomenon was the electric force. And from the very beginning, where people actually started to try to explain this, they seemed to get the sense that there was some stuff exchanged between the two, and now that stuff wanted to get back. So what they hypothesized, in fact this was Ben Franklin who hypothesized this, was there was something that was being traded between the two. I guess I should draw it up here, but he hypothesized that something called charge was being exchanged between them, with positive charges being exchanged, so that the plus was an accumulation of something, and the minus being a depletion of something. And the idea was, for some reason, they exchanged this, and then essentially, once they were done exchanging it, they had regrets and wanted to go back, and that's what was the cause of the attraction. Let's leave off there for today, but what we're going to find is that Franklin was totally wrong in some aspects of this and totally right in others, and we'll make a modification from there.